Hello, my name is Daniel. I'm here to present the paper, The Design, Architecture and Performance of the Tendermint Blockchain Network. It is authored by me, Enrique Fynn, Nenad Milosevic and Professor Fernando Pedone from Università della Svizzera Italiana in Lugano, Switzerland, and by Zarko Milosevic and Buchman from Informal System in Toronto, Canada. Tendermint is a state machine replication engine that tolerates Byzantine faults. It is among the first systems to adopt the classical Byzantine fault-tolerant consensus protocols to the blockchain paradigm. Consider the lifespan of blockchains started essentially by Bitcoin in 2009, Tendermint can be considered a mature technology. It was introduced in 2014 and it is currently in production used by several solutions in the Internet. Tendermint can be classified as a permission blockchain, with a known set of nodes called validators being responsible for determining the next block to be appended to the blockchain. The validators by themselves are determined by economic stakes, so by funds they bind to the blockchain. Tendermint is considered to be the first system to implement the slashing style of proof of stake. Originally proposed by Ethereum team, this approach not only rewards validators for the good work, but can also punish misbehaving validators by slashing their funds. Tendermint assumes that at least 2/3 of the validators are correct, or be more precise, 2/3 of the voting power distributed among the validators is on the hands of correct validators. Tendermint is the solution to the core of Cosmos, a network of interconnected proof-of-stake blockchains. In the paper, we overview the architecture of Tendermint and describe all the modules that are represented in the picture. Here, we only mention some of them. The mempool is the entry point of Tendermint. It receives transactions submitted by client and disseminates them to all the validators. The consensus module is responsible for ordering transactions retrieved from the mempool, grouped into blocks. When transactions are committed by the consensus protocol, they are appended to the blockchain. They are also delivered to the application that executes them. This is done through the ABCI, that stands for Application Blockchain Interface. The peer-to-peer module is responsible for the interaction between nodes in a partially connected network. All the communication is done via Cason. In the experiments, we adopted the latest stable version of Tendermint, considering August 2020, with default settings. We instantiate 128 validators and spread them among 16 AWS regions in all 5 continents. An additional non-validator node was instantiated in the 17 AWS region with 2 rows. As a seed node, it provided a random list of potential peers to validators so they can connect to those peers. As a learner, it delivered blocks of transactions ordered by Tendermint and computed performance metrics. The workload was generated by clients, a number of clients co-located with the learner, submitting 1K transactions. The reference workload considers 12 closed-loop clients per validator in a total of 1,536 clients. The first aspect we assess in our experiments is the overlay network generated by Tendermint when relying on a seed node. To build the network, nodes first retrieve samples of potential peers from the seed nodes. Then, each node tries to establish 10 outbound connections with potential peers. In addition, each node can accept up to 40 inbound connections. The graph presents the distribution of neighbors, that is, the number of connections established or accepted by each node in the experiment. Notice that all nodes have at least 10 established connections, and that most of the nodes, 64% of them, have between 10 and 20 connections. So they established 10 connections and accepted up to 10 connections. Some nodes accept much more connections, resulting in 30 or even 40 neighbors, but they are not the majority. Due to the high number of connections established, we can affirm that the generated network overlay is tightly connected. This is attested by the fact that 90% of the nodes are within 2 hops of each other. The remaining 6% are 3 hops from each other, which is the natural diameter. A second aspect that we analyze is the delay introduced in the internode communication with the adoption of Cason as communication means. To estimate this impact, we first measure the latency between the 16 AWS regions. This is their distribution presented in green in the graph. It would represent the approximate latency between nodes in a hypothetical fully connected network. Then, we estimated the internode latency in the generated overlay. Consider the shortest path between each pair of nodes. This is the purple distribution in the graph. We could then measure the impact of gossip in the latency between nodes. For example, while 74% of the regions are below 100 milliseconds for each other, only 41% of the nodes are within 100 milliseconds from each other, 30% less. And while essentially all zones are within 200 milliseconds for each other, 30% of the nodes need more than 200 milliseconds to interact. We now consider the performance of Tendermint in the absence of failures. We start from the latency, which presents a bimodal distribution that can be observed in the graph. The average transaction latency is of 345 seconds with almost 1 second of standard deviation. This happens because latencies are mostly concentrated in 2 intervals. In the first interval, around 41% of latencies were between 2 and 3 seconds, which is in line with the average block latencies, which is 2.5 seconds. About the same portion of transactions, 38% of them, have the latency around 4.5 seconds. This is close to the average duration of 2 blocks. To understand why this happens, we have to consider the journey of a transaction from the client until it is included in a block. The client submits the transaction to a validator, which disseminates the transactions to all validators via the mempool protocol. Among the validators, there is one which is responsible for proposing the next block of transactions. If the transaction reaches these validators before it proposes the block, the transaction will be included in this block. Otherwise, the transactions will only be included in the subsequent block. In other words, in our experiments, the mempool protocol was not fast enough to ensure that all submitted transactions are included in the next block. Some of them had then to wait for the subsequent block. This behavior observed with latency also influenced the instant throughput of a Tendermint. As can be observed in the graph, the purple line, the instant throughput oscillates a lot between blocks. But if you measure the instant throughput every 2 blocks, the green line in the graphs, we observe a more stable behavior, with values around 438 transactions per second. As block latencies are pretty constant, almost uniform, the zigzag variation in throughput can only be justified by the number of transactions included in each block. Recall that when a block is proposed, there is still transaction being disseminated via mempool protocol. The block, therefore, is not carrying all the transactions it could, resulting in lower instant throughput. These transactions eventually arrive, and combining with the new submissions, make the subsequent block larger, generating those peaks observed in standard throughput. So, as for latency, the operation of the mempool has a great influence on throughput. In the previous experiments, we had 128 validators submitted to the reference workload of 136 clients. To study the scalability of Tendermint, we applied the same workload to a smaller network, namely with 16, 32, and 64 validators in order to compare the performance. Using 16 validators as a baseline, the throughput achieved by Tendermint dropped by 3% with 32 validators, by 11% with 64 validators, and by 18% when comparing with the previous result with 128 validators. When you consider that we increased the system size by 8 times, this is a fair result. In addition, we can directly link the throughput degradation to the increase in the block latency when you have more participants in the consensus protocol. In terms of latency, the impact of the system size is more noticeable. From 16 to 128 validators, the average transaction latency increased by 27%. To the already mentioned increase in the cost of consensus, we have in this case to add increased delays to propagate transactions via the mempool protocol in a much larger network, and the mentioned effect it has on the latency variability. We are now back to the setup with 128 validators, and we will now consider scenarios with failures. We start by observing the impact of introducing the maximum allowed number of crash fails in the Tendermint network. So, during an experiment, we killed 42 validators, selecting specifically the ones that had more connections, so to improve the impact in the network connectivity. Despite the removal of 42% of the existing connections, the network remained connected, which highlights the resilience of the random overlay network built by Tendermint. In the picture below, we represent 3 snapshots of the networks in terms of the number of neighbors each node has. On the left, the original network with 128 nodes and an average of 22.2 connections per node. On the center, the network when the 42 crashes were detected, it took around 6 seconds, with 16 connections per node. Note that some nodes have less than 10 connections, which triggers the peer-to-peer module to establish new connections. In fact, almost 200 new connections are established, resulting in the distribution on the right with about 20 connections per node on average. So, not only the network was resilient to the crashes, they keep its connectivity, but also was able to reconfigure itself to ensure a minimal connectivity, so at least 10 connections per node. On the other hand, the impact of crashed validators on performance was huge. To understand the result, we have to recall how the Tendermint consensus protocol operates. Each instance of consensus has a validator assigned as the proposer. These validators propose a block of transactions that, in the absence of failures, will be accepted in a single round of consensus and then appended to the blockchain. This was the case of 64% of the blocks and 52% of the transactions, as can be observed in the picture. The validators detect that a proposal of an instance of consensus fault in using timeouts. They then agree that no block was proposed in the round and move to the next round, which is assigned always to a different validator. If this validator is correct, a block is committed in this second round. This happened with 17% of the blocks, resulting in much higher latency, around 8.5 seconds. Since we killed 1/3 of the validates, it might happen that the validator assigned to the second, third, fourth round is also crashed, and additional rounds are needed. As observed in the graph, one unlucky block requires 6 rounds to be committed because the validators assigned to the first 5 rounds were all crashed. As a result, the average latency was 2.7 times higher than in the 43 case, with a large standard deviation of more than 8 seconds, and throughput in the experiment dropped by more than 60% when compared with the failure-free experiment. Tendermint should tolerate not only benign failures, such as crashes, but also arbitrary or Byzantine behavior. We introduced in our experiments a particular type of Byzantine behavior, an equivocation attack. In these attacks, validators may send, in the same step of the protocol, distinct messages to different destinations. We introduced this behavior by configuring pairs of nodes to use the same validator key. In Tendermint, each validator owns a cryptographic key pair. The private validator key is used to send out the consensus messages, meaning the blocks of transactions the validator proposes and the voltage the validator casts. The public validator key is supposed to be known by all the participants and uniquely identify the validator. It also used to verify the authenticity of the message sent by that validator. When nodes share the same validator key, we get equivocation. This actually already happened in production with Tendermint in the Cosmos Hub network as a result of a configuration mistake. The link to the blog post is present in the slide. When two nodes share the same validator key, they may propose and sign different blocks of transaction in the same instance and consensus, and cast conflicting votes for different blocks in the same round of consensus. For the consensus algorithm, this is the same as a single validator double signing, a behavior that is punished in Tendermint. We start introducing this behavior, so this malicious behavior, with few validator keys in the network, but we didn't observe any noticeable effect. So we ended up with 64 validator keys being shared by the 128 nodes. So you have 2 nodes per key, which means that all validators are Byzantine. Even with this aggressive attack, we didn't observe any violation of the safety of consensus, or in other words, we didn't observe forks in the blockchain. But we did observe some impact in the performance of Tendermint. First of all, the average latency with 128 nodes sharing 64 validators keys increased by 55% when comparing with the fail-free experiment. Notice that the comparison is made with experiment with 64 nodes, because even though we had 128 nodes, we only had 64 validators. For most of the blocks, 9% of them, and for 86% of the transaction, the attack did not succeed, and consensus was achieved in a single round with regular latencies. But for 10% of the blocks, the first round of consensus did not decide a block. This happened because 2 distinct blocks were proposed in that instance of consensus by the 2 nodes running the same validator, and none of these 2 blocks managed to get the node votes in order to be committed. Then, in a second round of consensus, one of the blocks was chosen by 2/3 of the validator and was committed. Transactions included in these blocks were affected with increased latency, around 7.5 seconds, as can be observed in the picture. And as a result of the higher latency of these blocks, throughput was 19% lower in this experiment when compared with the failure-free experiments, also with 64 validators. We conclude our presentation recalling that our paper overviews the main design goals of Tendermint and associates them to its design and architecture. We also present a detailed performance evaluation of Tendermint in a realistic environment, a geographically distributed setup with 128 validators, consider fail-free executions and executions affected by crashes and a specific form of Byzantine behavior. From the results highlighted in this presentation, we can derive 3 major conclusions. First, Tendermint builds a well-connected and resilient network overlay. In fact, the removal of almost 1/3 of the most connected nodes did not disconnect the network. Moreover, after the crashes, the node established new connections, thus repairing the network. Second, the crash of 1/3 of the validators turned out quite harmful to performance. This impact is related to the way the consensus algorithm selects the proposer, which is a rotating rule in Tendermint. We have to mention that there is no economic advantage for a Byzantine validator to pretend it has crashed, but with that, it can definitely affect the performance of the protocol. Third, inducing Tendermint validators to misbehave under equivocation has proved difficult. It required going quite beyond the limit of Byzantine validators tolerated by the protocol, and even so we could not observe forks or safety violations. We attribute this resilience of Tendermint to failures and Byzantine behavior to adoption of gossip as communication means. Gossip makes it hard to design attacks that require sending specific messages to some nodes and different methods to others, as the dissemination of messages is usually unpredictable. I thank you very much for watching this presentation, and I'm open for questions from the audience.